the outline for this chapter. So we'll talk about the concept called the photon. And the second one is the photoelectric effect, which is a very important result in the modern physics. And next, we'll talk about the quantum scattering. And after that, this stuff is about the quantum mechanics, the Schrödinger's equation, Heisenberg uncertainty principle, and so on. So, first of all, it's about the photon. So in 1905, as I mentioned, Einstein has written 3 papers. One is about the special relativity, and the second one is about the photoelectric effect. And he is actually awarded the Nobel Prize for the photoelectric effect. And actually, E equals HF is a result from the photoelectric effect. So at that time, he tried to fit the photoelectric effect with a mathematical model, and he actually find that E should be equals to HF. F is the frequency of the light, and H is a famous constant called the Planck constant. Of course, it is discovered by Planck, and Planck discovered this constant in another experiment called the blackbody radiation, and he really needs this constant to fit the distribution for the blackbody radiation, but we will not cover that because it is not so strongly related here. But actually, Planck constant is shared in these 2 results. And Einstein proposed the term quanta at that time. At that time, there's not photon yet. They do not call it photon yet. At that time, Einstein called it a quanta, because as you know in chapter 33, we know that light is EM wave. So of course, light is wave. But whenever we consider the light as wave, then it cannot solve every problem. We cannot describe all the phenomena in the world. So Einstein really needs the concept of quanta, which means that light can be some sort of particle, which means it is an energy package of light, so that it can use this model to really describe some of the phenomena. And in this equation, it tells you that the total energy of a photon is only related to the frequency. When the frequency is higher, the total energy in the photon is higher. And sometimes we will use this expression rather than E equals HF. H bar is the reduced Planck constant. We just divide H by 2 pi. So in quantum mechanics or the modern physics, some of the formula, if we use H bar, it will look lighter. But some of the equation, if we use H, it will look lighter. So it depends on what is the formula you need to use. So, but here I just tell you that there's a constant, Planck constant H, which is 6.63 times 10 to minus 34 joules/second. So, and if you divide it by 1.6 times 10 to minus 19, so it will be converted to in EV as EV second. So you just divide it by 1.6 times 10 to minus 19, which is the elementary charge. And here, if we use H bar here, then it is something like E equals HF, E equals HF. So we can just divide by 2 pi and multiply by 2 pi. So the whole formula doesn't change. So H over 2 pi is H bar and F times 2 pi is omega. So actually, sometimes we will use E equals H bar, which will be more convenient. Okay, here comes a simple example. So a sodium vapor lamp is placed at the center of a large sphere of absorbed all light reaching it. The rate at which the lamp emits the energy is 100 watt, and emission is entirely at the wavelength of 590 nanometer. At what rate is the photon absorbed by the sphere? So the rate of photon emitted is the power emit divided by the energy of a single photon. And it is equal to P emit, and E is HF. And we also know that C equals F lambda. So 1 over F is nothing but lambda over C. So we can write it as P emit over HC times lambda, because we are given the wavelength, which is the lambda. So we can write it as 100 rad times 590 times 10 to minus 9 over 6.63 times 10 to minus 34 times 2.998 times 10 to 8. So the answer is 2.97 times 10 to 20 photons per second. So any questions? So it is pretty simple. Okay, so next we talk about the photoelectric effect. So this is this figure shows the apparatus used to study the photoelectric effect. So it looks a little bit complicated, but you can just ignore this part, because this part is just to generate a voltage between this point and this point. So if you cut this down and without loss of generality, you can regard this one is a ground, and this is a battery, this is another battery. So it's a resistor, so that if this point is sliding on this resistor, so you can choose a voltage between this node and this node. So maybe if this one is VB and this is also VB, so this node it will be plus VB and this is minus VB. So then we can choose a voltage between minus VB and VB, and this is ground. So this is just for choosing a voltage at this point. and this is just a ammeter and voltage meter. So it's just for measuring the voltage between this node and this node, and measuring the current going in this loop. So it does not really related to the phenomenon itself. So you can really ignore it at this moment, so that the figure will look easier. So the point here is that this is a plate. This is a plate. We have a target T here, and then we try to inside incident. There are some incident light going from there, so that to shine on that, so shine on the target. And actually, this loop is not closed. It's not closed. It is really open here. It is really open here. So without the light, there should be no current, because there's not complete path in between. But the phenomenon is that if you try to incident some light here, there may be some current, because the light will collide with the electron, and the electron will absorb the energy, and then it can try to go from the target to that node, and it will really form a complete loop. So the point here is that it is really related to the frequency or the energy of the photon, but not the intensity. In chapter 34, you know that there are so-called light intensity, which means that you make it more photons, then the intensity of the light will be larger. But actually here is not the case. If you just remain the frequency of the light low enough, even though you increase the intensity, it will not generate the photoelectron, and there is no current. And actually, the point here is that the energy absorbed by the electron should be larger than EV stop, which means that as we choose a voltage here, which is minus V stop, or maybe minus V0. Suppose we choose a voltage here, which is minus V0, which means that the voltage at this node at T will be higher than here, than the right node, so that there will be a electric field between the T and the cup, and the voltage at T is higher, so that suppose I write it like this, and maybe you just ignore the bottom and the top and the bottom plate. You can feel that this one is minus V0, and this one is 0. As I mentioned, this one is 0, because this is just a relative voltage, so it doesn't really matter if it is 0 or something. But the voltage difference between T and the cup, is V0, and this is higher, so there will be a electric field pointing to the right here. And in this case, the electron is a negative charge particle, which means that if it is trying to move from the T to B0, there will be a force acting to the left on the electron. So the electron will become slower and slower. But the point is, if K max of the electron is as large as EV stop because the voltage is V0 and the charge of the electron is E or minus E. So the energy potential between T and the cup is EV0, or here is a EV stop. So the kinetic energy must be larger than EV stop so that the energy can go to the cup and form a complete loop, and then you can measure a current going through this loop. If the kinetic energy is smaller than EV stop, the electron will emit from the target and go halfway and then go back. Okay. So that's the phenomenon here. Oh, Kmax means the maximum kinetic energy that the electron will go back. This is what it defines here, but it is just a notation. It doesn't really matter. But so I need as a Kmax. There may be some other meaning, but it's not really. But here it means that the most energetic ejected electron that are turned back just before reaching the collector. So we call it Kmax here. The max has this meaning. So next, we also find that if the frequency f of the incident line is vary, the associated stopping potential V stop is also varying, which means that if we try to, so the x-axis is the frequency of the incident light f. So we try to change from here, and here. There are totally 5 points for this graph. And we actually find that the V stopping for this experiment is different, which means that here, suppose we have a fixed frequency. We have a fixed frequency for the light, and then we try to slide this. Suppose the voltage is high enough, there will always be a current going through this. So, but as long as you stop at a certain point, the current going through the loop will suddenly go to zero. This is a very interesting phenomenon because it does not stop gradually or linearly. And actually, this V stop, this is a V stop we mentioned, that suddenly there will be no current can going through the loop. Because, as I mentioned here, the kinetic energy for the electron absorbed by the light will be fixed value. And if you further decrease the voltage at this point, which means that the potential energy between the target and the collector will be larger, then it will be more difficult for the electron to reach the collector. So this graph tries to vary the frequency of the incident light and also measure the corresponding V stop, the stopping potential. And actually, it is just like a straight line. It's just like a straight line, and certainly cutoff frequency f0. So here, when V stop is zero. This frequency is called the cutoff frequency, which means that when we make this point and this point have the same potential, then the frequency of the incident light that can barely have photoelectric effect is called the F0, the cutoff frequency. So here, the corresponding energy that need to overcome this phenomenon is called the work function phi, big phi, and actually we'll find that it really satisfying this formula. So HF is the energy for the incident light, and work function is the minimum work that needs to be done so that the electron can go from the target to the collector. So after subtracting this work function, all the energy will go to the kinetic energy of the electron, and this electron is called the photo electron, which means it is you you have an incident light so that you make the electron to be a free electron. If the incident light have a smaller energy than the work function, then you cannot generate the photoelectron. And in the first page, we wrote that HF equals Kmax is EB stop plus phi. So we subtract phi on both sides, and this one cancel. And then we divide E on both sides, so that we will have this equation. So it's something like y equals mx plus b. So this y equals mx plus b, and f is the x, y is the v stop, y is the v stop. So it's actually a straight line to fit this phenomenon. So Einstein and Planck fit two phenomena with actually the same Planck constant. Because before E is already a known, and actually phi is related to the material, of the target. So here's another sample problem to find the work function of sodium Na from the figure. So this. So find the work function, which means that so here when f equals f0, v stop equals 0, which means this point. So we'll have phi equals hf0. So H is 6.63 times 10 to minus 34 times 5. So this point is roughly 5.5 times 10 to 14. 10 to 14. So the answer is 3.6 times 10 to minus 19 joule. And it's actually 2.3 eV. So any question about the photoelectric effect? So next, we talk about the photons have also momentum, and next is about the quantum effect. So Einstein won the three paper in 1905, and he used 10 years to finish the general relativity until 1915. So after he finished the general relativity, he come back to the quantum theory. And in 1916, he extended his concept of light quanta, or now we call it photons, by proposing that a quantum of light has linear momentum. Because in classical mechanics, for particle, there are some variable specially designed for particles, which is the momentum in 3 dimensions, and also the energy. But for wave, we have the wave number in also 3 dimensions and the frequency. So just now we already know that E and omega has some sort of relation, like E equals h bar omega. So whether the K and P have some sort of relation. If it is this, then we can claim that there is so-called wave particle duality, 波粒二象性. And actually, it's something like that. So he proposed that the P should be like this. So you can regard it as E equals PC. If you remember in the last chapter, I tell you that E squared equals PC squared plus MC squared all squared, something like this, for a particle. And MC squared is the rest energy, and P is the momentum. Of course, consider the relativistic effect, which means it is not only mv but it's gamma mv. Here for a photon, the mass for a photon is 0. Mass for a photon is 0. So that this term is 0, then E should be equals to PC. So we substitute E equals PC into actually we reallocate the variable so that P equals E over C. And as we know, E equals HF, so we substitute E equals HF, so that we have something like this. And also we know that C equals F lambda. C equals F lambda. So that finally we can write that P equals H over lambda. P equals H over lambda. And in chapter 32 or 33, we know that K equals 2 pi over lambda. K equals 2 pi over lambda, which is the wave number. So P equals H over lambda. So we divide by 2 pi and multiply by 2 pi. So that the first one will become H bar and the second one will become K. So we can also write it like this. But in the textbook, it does not mention the H bar notation. So, but I just put it here because in the Schrodinger equation, you know that if we use the H bar, the equation will look cleaner. And this is the momentum. So just now I mentioned E and omega. E is the variable for particles. Omega is variable for wave. Then they have some sort of relation. And P is for particle and K is for wave. And now we know that P and K also have some sort of relation. So for light, we know that there is some sort of wave particle duality. And next we discuss about the quantum effect, the quantum effect, not quantum effect. Quantum effect is about this graph. So here we also shine some rays to a target, but now we use X-ray rather than visible light. So compared with visible light, X-rays of course have a higher energy, as you know. If you don't know, if you can't really remember, you can check the first two lines in the Maxwell equation. I've showed the Maxwell's rainbow. So gamma ray will have the highest energy, and X-ray followed by it, and so on and so on. So X-ray have pretty high energy, and so the high energy, which means that the frequency is high and the wavelength is low. That's why we can use X-ray to have to check that whether a bone are good or not, because it can really go through the skin and fresh, something like that, but it cannot only go through the bone, so that we can use it to see through something. And here we use the X-ray to shine on the target, and of course the X-ray is also a sort of EM wave, and it can also be regarded as a photon. And the phenomenon is that when the X-ray collide with this object, then it will scatter in different angle. And we find that if the scatter angle phi here is 0, then you can see one peak. If phi is 45 degrees, you can start to find two peak. And if the scatter angle goes to 90 degrees, the two peak spread wider. And actually the original peak remains the same, roughly the same at here, and here. So the lower peak remains the same, but when the angle becomes larger and larger, 0, 45, 90, 135. The second peak will become higher and higher, which means that the energy is lower and lower. So we can really measure the delta lambda between the two peaks. So we try to explain this phenomenon. It is something like this. So suppose we have an X-ray with wavelength lambda collide with an electron, which is stationary, and if the wave can go through, then it is actually skip the electron, so that the wavelength doesn't really change. But if the wave is scattered in an angle phi, which means that it collides with the electron, so that it is really a particle. You need to regard the X-ray as a particle, as a photon, so that it can collide with an electron, although it doesn't really have mass. But actually, the photon of X-ray collide with the electron, so that it is a collision, so that the X-ray go in another angle and the electron go in another angle, and it should satisfy the conservation of momentum. And if it is 180, which means that the electron go in the x direction and the X-ray go back. And actually, we with the conservation of energy, because we can assume that there's no loss in between. It is a fully elastic collision, so that this is the original energy of the X-ray, and the X-ray become so, which means that some of the energy is absorbed by the electron, so that the electron have the kinetic energy K, and the X-ray will have a lower energy because the energy should conserve. Next, we need to consider the relativistic effect, so that the kinetic energy should be gamma minus 1 times the rest energy. So the conservation of energy become like this, and of course C is F lambda and gamma is the Lorentz factor, which we learned in the previous chapter. Next one is the conservation of momentum. So this is the original momentum. This is the momentum of the photon. So the momentum of the X-ray should originally be h over lambda, and it becomes h over lambda prime after the collision. And the electron have some sort of kinetic energy, and also have the momentum, which is gamma minus 1 mz. So if we try to extract it in x direction and y direction for the momentum, then we will find that let me see. Okay. So that for x direction, original, it is all h lambda is all in x direction, so that h lambda is 0. For h over lambda prime, phi is this angle, so that in x direction cosine phi and y direction sine phi. And for the this one should be okay. This one should be gamma mv. Gamma mv is the momentum rather than gamma minus 1 mc. So this one should be gamma mv, and this one is theta. So in x direction, it is cosine theta, sine theta, but with a minus sign. So if you really solve this equation, actually, first one, second one, and the third one, you can really find that it will look like this. It will look like this. I do not show the step here. I have read it in my notes, and I will share with you after the lecture. It's just some algebraic calculation, because actually lambda prime are unknown. V is also unknown. No. Lambda is known, but yeah, lambda is unknown. But actually, finally, we only need the difference between lambda prime and lambda, so that we have three equations, and finally we can really reduce the v, reduce the phi, reduce the theta, and finally we can get this one. A simple idea is that you move this term and this term to the left, and then you square both equations and add them together, so that cosine theta square and sine theta square will become 1, so that we can eliminate theta first, and then so on. To actually, it takes some steps to really derive it. But if we consider what is the meaning of this, is that according to this equation, which means the conservation of energy and conservation of momentum should always be satisfied if there are some particle collision. And we'll find that if the scatter angle is 0, which means that it goes through, then the lambda doesn't change. But if phi becomes larger and larger, then cosine theta can only be smaller than 1. So cosine phi can only be smaller than 1. So 1 minus cosine phi should be larger than 0, which means that the delta lambda should always be become longer and longer, which means that the energy of the X-ray should always be absorbed by the electron. And here we define the term h over mc, which is the Compton wavelength. Here, h and c are also constant. H are Planck constant, c is speed of light, and the mass is the particle. Here is the electron for this derivation. So if you substitute the mass of the electron inside, you can find the Compton wavelength for the electron, which is roughly around 2 picometer, around 2 picometer. You can just use a calculator to find it. And in this case, it's also an experiment to show that you need to regard the light as a photon in some case, so that it can describe some of the phenomena.